All right, let's get started. So, new topic today. And again, the focus of this class we've been talking about a lot is trying as much as we can to live in the Laplace domain, but to actually get time domain response characteristic and that type of stuff. So what we're going to focus on is what are the things a real world system could possibly get or experience, and then look at the performance of that system. Now, the difficult part is a real world system. You're not going to necessarily get these really easy inputs to say, oh, it's a unit step or it's a ramp or something like that. They tend to be a lot more complicated and a lot more transient. So you might have a little bit of a bump and then you might have a linear ramp, or you might have a ramp and then stop and then continue. It just depends on what you're trying to accomplish. So the idea is, whoops, this. Let me just make sure we're recording. Yeah. So the idea is, as much as we can, look and see what would be our worst case scenario. If our worst case scenario shows that the system is responding the way we expect it to, then it should respond to just about any other input. And then the other thing is we want to live in our time domain, but we want to stay in a Laplace domain because partial fraction expansion is just so much work. It's not necessarily hard math, it's just tedious. So we're going to look a lot at this presentation, if you will, and looking at our response to time characteristics. So we talked a little bit about transient and steady state response. One is the forced input and one is the natural response of the system. We're going to look at our performance and then see if a system responds reasonably. So we're going to test it and then see, does that make sense with what we have for those test signals? And then we're going to look at what our steady state response is and our transient response. Those are time domain responses. So steady state, final value theorem works really well. Transient response is what decays over time. So doing the transient response sometimes takes a little bit more effort to go ahead and get our results. Oops. All right, so we'll look back at this a little bit just to make sure that we formalize this, because we talked a little bit about it last semester, we even discussed it a little bit this semester, but we really need to nail it down this semester because we're going to be doing what are called root locus plots, which are heavily reliant on understanding poles and zeros. And then more importantly, and again, we talked about this last semester, is based on the location of the poles and zeros, how do we anticipate how that system is going to respond? So our output has two output parts, if you will. We have a forced response, which is the steady state. The forced response is as a result of energizing our system, providing it some sort of a power source or signal so that we get an expected output or close to what we want for an output. So we are literally driving that output to what we want it to be based on the input that we provide. The natural response is the system is configured in a way, and there's not much we can do to change the characteristic of the natural response. That always decays over time, but that's basically the system's way of saying, I am changing and I may or may not like the change, so I have to adapt my system to go ahead and get this response. So you sum the two and you have the output. So remember what a pole is. A pole is of your transfer function. This is just for the transfer function because we already talked about BIBO stability, bounded input, bounded output. So we can look at the poles of the transfer function, and that transfer function is going to tell us if the output is going to be bounded based on a bounded input. So our poles are the roots of the denominator of our transfer function. All it is. And our zeros are the same, except they're the roots of the numerator of our transfer function. So if you have a root, remember that's when you evaluate at that root and the equation evaluates to zero. So with a zero in our transfer function, we're going to get our transfer function evaluating to zero. So it's 0 divided by something is going to be 0. In the case of a pole, if we evaluate at that root, then our transfer function goes to infinity because we have a 0 in the denominator. So we do our pole zero map, right? We love our pole zero map. They're easy to follow. They provide a lot of information. So we'll just look at that graphically. And then again, the reason why we look at a transfer function, because we can see over here that this, what type of system is this? C of S, this is our output. Can you tell just by looking at the transfer function? Actually, the transfer function is way up over here. Let me move this out of the way. Can I look at this and tell what type of system response this is going to be? Is it a stable system, unstable system, or marginally stable system? Marginally stable? Unstable? Anybody want to guess stable system? That's all three. It actually is the one that you didn't guess. It's a stable system. Because remember what determines a stable system? All poles have to be negative numbers. What is the root of the denominator here? -5. I think why one of your classmates got caught up saying this is a marginally stable system is because I saw the S here. The S is from the input. R of S, the input, is 1 over S. The actual transfer function itself is a completely stable system. So as long as I provide a bounded input, I'm going to get a bounded output. A unit step is bounded. So this is a a stable system. Now I'm all confusing myself. So now I'm going to go ahead and multiply that by my input, which is just a unit step. Here's my actual output function. Do partial fraction expansion. I get my A and my B term. A is 2/5, B is 3/5. So my C of t is 2 over 5 plus 3/5 e to the minus 5t. So this is where we have to be careful because my unit step here did not, I can provide, so remember, if I had an S term in here, if I have an S term in here, the 1 over S hitting the integrator would make that output blow up to infinity if you just left it go there for a long period of time. But over here, I don't have that S. So all I have in the output is a forced response, right? Or steady state. That becomes 2 over 5. That's bounded, isn't it? It doesn't continue to blow to infinity. It just stays at 2/5. So this is a stable system. The other one is my natural response. And that's the term that decays away. So now we're going to plot the poles and the zeros on our S-plane. And we see that we have a pole as indicated by an X and a 0 as indicated by a 0 shown on our map. All I really care about is what are the locations of the poles. If the poles are in the left-hand half plane, and all poles are in the left-hand half plane, this is a stable system. Okay? And that's the poles of the transfer function, not of the output function. All right, so we talked a little bit about this. The bounded input, bounded output, we see that the system doesn't approach infinity. It just goes to 2/5 over time. If it also, so the other thing about Bible stability is if you get to a point in your system where you can't control it, that also may be considered an unstable system. Meaning the example that I use is, okay, I'm filling up a tank. The tank is 10 feet high, but the steady state that I get an input is going to eventually try to get to 12 feet. So what ends up happening is the water level in the tank exceeds the height of the tank, and it ends up spilling on the floor. That to me is an uncontrollable system because it just overfills the tank, and that's not exactly what you want it to do. And by the way, most tanks, not all tanks, but most tanks have a cap, right? Very few tanks are uncovered unless it's like something you don't care if debris gets into it. So if you were to go in a process plant, most of the time your tanks are actually encased with a cover so that you know that whatever's in that object, whatever's in the tank should be whatever you placed into it. Once you remove the lid, you can certainly do that if you have to do samples, like anybody here making beer or ever heard of making beer. You can see those tanks, they actually will brew beer inside of a tank, and they have a small opening so that they can add or subtract ingredients, but then they also do some sampling. So that's a case where they close a tank because they don't want stuff coming from the outside. The other thing too is temperature control, right? It's much easier to control something if you have a cap where you can maintain some of the heat. Anybody here cook rice on a regular basis at your house? What do? Rice will cook without a cap on, but you put the cap on it, and then you know that the temperature inside will get a little higher, and you can control that much, much better than by taking the cap off. So that's just one of the things, like if you get out of industry, you'll walk around and you'll see tanks all over the place, and they're covered. That's different though. Most tanks are not what are called pressurized tanks. Okay. A pressurized tank is a much more higher end piece of equipment. So if you were to go to like your Home Depot, they have pressurized tanks for your house where you're trying to maintain a certain pressure inside the water lines in your house. So inside those tanks, they fill up with water, but then there's a baffle to help maintain pressure, so that as it fills up with water, the baffle expands or contracts. So it maintains a nominal amount of pressure. That thing is welded and it's built fairly heavy duty. Where if it's just a standard tank where you're just trying to fill it with water, normally it's a pretty simple, basic piece of equipment. So from a cost perspective, non-pressurized tanks are much, much cheaper than actual pressurized tanks, because the air pressure itself is, is pretty overwhelming. So if you're looking at a process, most of the time, not all the time, but most of the time, your systems aren't going to be pressurized. I mean, your tanks aren't necessarily pressurized unless it's like an expansion tank or something like that. But if it's just a makeup tank, that's the concept of a makeup tank. You just have water that's sitting there, and then you take it in and you pump it into a pressurized system, for example. Like in a steam cycle, you definitely have pressurized systems there because you're trying to run the steam up to 2000 psi or something like that, and then you condense it back down, and actually you pull a vacuum on it. Sometimes it's less than vacuum, because do you remember in your thermodynamics class, I can pick on Pat on this one, how do you determine the maximum efficiency of a thermal cycle? Carnot efficiency is a theoretical efficiency. What's the Carnot cycle based off of? Have you all had 433 yet? All right, perfect. We're gonna have to yell at Dave now. 2 years ago. 2 years ago? What is Carnot efficiency? The absolute best efficiency is going to be based on the temperatures, right? So the higher the temperature you can get, and the lower the temperature you can get, is your Carnot efficiency. That's like the theoretical maximum efficiency you can have. So if you think about from a control perspective, why do we want to run at superheat levels at really high temperatures? And why do we want to have our condenser? Because we want to go ahead and condense our water at as low a temperature as possible so that we can maximize our Carnot efficiency. So that's why some boilers today, you can run 700-800 degrees. If you're in a steam cycle at a power plant, they're pushing 1,000, sometimes 1,100 degrees of temperature. You got to run it up to 2,000 psi, because you have to be able to bring that steam back to water at some point. So if it goes into the steam turbine, before it gets there, it's got to be actual water, and you don't want it to be at you don't want it to be at 200 degrees. So you actually have to pressurize it pretty high, because you don't want a huge delta between the two. By the way, anybody know why temperature limits 1,100 degrees or so kind of limits of most thermal cycles? It's a more obvious answer than you think. What kind of metals can handle 1,100 degrees and not warp or change their characteristics? Lead boils at what, 350 or something like that? Gold boils at low temperatures. So you need really, really fancy metals and alloys to be able to get to those temperatures. So you're getting to the point where you can't get to those level of temperatures and be able to work. So at one point there was research on ceramics, because ceramics you can get to thousands of degrees, right? But the problem is you still needed a case that can handle those temperatures. So if you built your case out of ceramic, then somebody walks by and hits it with their elbow, and then you crack the ceramic, because that's the problem with ceramic. Handles ultra high temperatures, but it doesn't have the ability to handle, any real force. So I'm not sure. Let me look and see. Look on Edge. Usually gas turbines are the highest temperatures you can do in steam cycle. It may have gone up. Yeah, so this is 1600 degrees. I must have been doing Fahrenheit, but 1600 degrees Celsius is sort of the highest turbine. I've never even heard. Mitsubishi does make them, but they say this gas turbine is their most advanced. So maybe that's a research thing that's still happening, but you're getting into really, really crazy temperatures here. The ones that I'm used to is GE, I think it's 7FA. So that's the inlet temperature. What's the outlet temperature? That's the firing temperature, but the I guess I can't find it. Anyway, that's not really relevant to the discussion. It's just kind of interesting because if you ever get a chance to tour, there's a GE facility just outside the airport in Bangor, and that's what they do. They make the turbines and the turbine blades, or they do retrofits. And I used to know somebody who was a buyer for their equipment, and he would have to buy really fancy alloys. He could never buy them stateside. He'd always have to go to Japan and get all these fancy alloys. This is, I don't know, 10 years ago that I talked to him, but these are multi-million-dollar orders for a slab of steel, not much bigger than that desk that's sitting in front of you. Because again, just really stringent temperature, and these have to run at 1100 degrees, 1200 degrees temperature for years and years and years without having a lot of maintenance on them. So pretty important. All right, so let's get back into the topic at hand. Don't want to get too much sidetracked. But again, we really didn't care about the input. The input had no impact on the stability unless it's a marginally stable system, right? So we only talk about with the marginally stable system is if it's for poles or P's on the J omega axis. Remember, a pole at S equal to 0 is a pure integrator, and a pole or two poles on the J omega axis is one where you're going to have a natural frequency. So when you excite something at a natural frequency, you get a sine wave that eventually gets bigger and bigger and bigger. The crystal oscillator discussion that we talked about. So those are our concepts there. And so now we look at the different systems. So this is our system that we had that we just analyzed. Here's our input pole. Here's our system 0. So this is the numerator. And here is our system pole, which is the denominator term. And then if we have the three parts that make up the J omega axis, or the S plane, we have our 0 right here, which we determined already doesn't affect stability. We have our 0 at this location. So you can see here that this has nothing to do with that. That just has that just has to have an effect on the magnitude. And then this one actually has effect with the time response. So what you see is this term over here just does the steady state output. That's the force response. That one is what we see in the output. The 0 over here only affects the magnitude of those two terms, how high up they go. It has no impact on the time domain response other than amplitude adjustments. The pole that we have over here, because that's the S plus 5, that does have an implication on the time domain response. So the 0 has no effect on how long a system takes to get stable, but it does affect how high the terms can get. So we talked about our force response and our natural response already. Again, this is all determined from our input pole, and this one is determined from our system pole. So our input function is our input poles, which we usually don't care too much about. But if you really want to know, that's what determines our force response. Our system's poles is the natural response. That's the one hopefully that decays with respect to time. And our system poles and zeros help impact what the amplitudes are going to be for both those natural and forced responses. So let's build our pole zero map. Our pole zero map has three parts that are important to us, or our S-plane. We have our left-hand plane or left-hand half plane, depending on which book you believe, your right-hand plane, and your J omega axis. So everything over here is denoted left-hand plane. Everything over here is denoted right-hand plane. J omega axis is just the axis itself, so it lives only on the J omega axis. So we're going to denote, or we're going to identify in this class, this is pretty consistent, poles as X's on our pole zero map, and zeros as zero, or zeros are going to be our zeros on our pole zero map. So these are the three sort of key bullets to determining stability of our system, Bibo stability. So if all poles, every single pole that you see, if it is in the left-hand half plane, then your system is always Bibo stable. So if all poles are there, it's a stable system by default. Notice the language term here, a subtle change in language. If any pole is in the right half plane, the system is Bibo unstable. By the way, let me ask a question. Did I have these slides? I forgot. I thought I put these up last week. Are these slides? They're not there. Okay, let's do that really quickly. So I know some people are keeping track with notes. I apologize. I thought I had put this up on last week because I wasn't sure if I was going to cover it, but I'll do that right now. Takes me just 1 minute. Sorry for the side thing here.
Will we have a test next week?
No, week after. I have a test next week in one class, unless you'd rather have test next week. All your friends and I guess. Yes, yep. That's the current plan. All right, let's go back to here and let's bring this back up. This is number 5. Oh. Okay. Let's just make sure that this is the actual one. Yes, second order systems, I believe. Yes, so it should be up and available now. Let me just, yep, should be good to go for under today's class. Apologize for not being organized for that. All right, so continuing. So last one we covered was if any pole, all you need is one. If any pole is in the right-hand half plane, that one term goes to infinity with time. So you have an unstable system. And the next thing is if any pole is on the J omega axis, again, any pole, the system is marginally stable. Why is it marginally stable? Because the output could be stable or not. It just, you need to know what the input is to determine the input. So you just give it as a marginally stable system, and then you tell the owner, buyer beware, because if you hit it with a unit step and it has an integrator in it, it's eventually going to be unstable. Or if you hit it at its natural frequency, then it's going to be unstable. So you can tolerate marginally stable systems, provided you're going to have limits on your inputs, which means you're never going to get into those bounds. Okay, Pat, do you have a question or?
Yeah, it's just on the J omega axis, not like the J omega. Like it was 3 5s. It's only marginally stable, right after that.
Has to be on the J omega axis, anywhere on the J omega axis. It doesn't have to be at 0. It can be plus or minus J3, plus or minus J5 million. Anywhere on the J omega axis makes it a marginally stable system. So, okay. So, go ahead, B.
So,
Morning.
what if we have one pole on the right and one pole on the left?
So you have one pole on the right-hand half plane.
Yeah.
It's always unstable. Any pole, that's why there was a caveat. Any pole in the right-hand half plane, that's the second one, makes it unstable system. Because no matter what, so remember what makes a system stable or not, if it's a marginally stable system, this output could be stable. I just need to know what the input is. If you have a pole in the right-hand half plane, it doesn't matter what the input is, the system is unstable. So that's why it's irrelevant to know what the input is. If it's got a pole in the right-hand half plane, it always is going to be an unstable system.
Even if we have one pole here on the left and one pole on the right.
Doesn't matter. If you have one pole on the left and one pole on the right, it's an unstable system. Because the reason being is if you remember from your Laplace table, if I have one pole here, this becomes e to the positive AT. A has to be greater than 0 for it to be a right-hand half plane. And you can see as t increases, what does e to the AT do? Gets bigger and bigger and bigger. Where if it's over here, where a is less than 0, then you have e to the minus AT, right? Or e to the minus some negative number. And as t increases, that goes to 0. Because if it's a negative number, we know we end up with something like this, right? A negative number up front just means put it in the denominator. And as e to the AT increases, 1 over e to the AT goes to 0. So anyone over here, the right side rules the roost. Because over this one doesn't cancel it out, right? This one is going to 0. This one's going to infinity. 0 plus infinity is still infinity. All right, so poles and zeros can be complex, but they don't have to be. They can be complex, but they can be purely real. And they can have no real part, right? So we're going to have a couple of terms. Our sigma term is the real part. And we always go with omega over here. Why do we go with omega? Why do we call that omega? That's the radian frequency. So if you're going to go back into the time domain, you'd either have a sine or a cosine of omega t. So the reason why we call it omega is it's actually the radian frequency of the sine. Over here, this is just the, hopefully, exponential decay. So that's the real part of the term, and that is what gets affiliated with the e to the t term. It's the e to the alpha t term. So because poles and zeros can have real parts and imaginary parts, my axis has to be real and imaginary. So I have my sigma axis, which is my real axis, and my j omega axis, which is my complex axis. And for convenience, we always say, even in circuits classes and all this stuff, we always say this is the real axis and this is the complex axis. We always represent the x-axis as the real axis and the y-axis as the complex axis. All right, so let's take a simple example. So we have, sorry about that, folks. We just seem to have lost our screen just disappeared. It's flashing, but I'm not sure. Just bear with us for one moment, because what's that? Well, I'm wondering if it's actually shutting off because maybe it got overheated. I'm not exactly sure. Just clicked off. Try that again. Can you all hear me? It says I have low system resources. It's the story of my life. Low system resources. Get up at 5 and go to bed at 10. Try to get some sleep. I'm envious of Pat. Pat got up at 7:40. It's like a dream in my house. You didn't go to bed at 10?
Same.
Yeah, if I got up that late, it'd be like, I need food, Dad. Get me food, you know. Your day will come. Then it's a scramble. Oh, sorry. All I have is you know, some Doritos and maybe a piece of cheese for breakfast. So you try to give your kids something remotely healthy. He's got to spend a little bit of time. Sorry, I'm just going off on a tangent because we still don't have our screen back. So hopefully it'll wake up. Looks like I'm seeing some coloring here. Maybe not. I'm just not sure why it's not toggling over. Here we go. All right, we're back in business. Again, apologize for the side. Okay, so we have not the easiest transfer function. We could figure this one out pretty easy. We could just do quadratic equation for that, right? Because it's an S squared term. That one would be pretty easy. This one, when we have an S cubed term, is much, much harder. Or S cubed and above is a much, much harder term to determine what the roots are. So you're welcome to use whatever tool you want. I like MATLAB, again, because MATLAB just makes things really obvious and you can see it. But your calculator can do root solving. You just probably want to set it up with CSolve, because if you have any complex roots, you'll have to go from there. So let's type in our MATLAB scripts and hopefully get the same results. Let's see. So it's roots. And in MATLAB, you open parentheses that you're using a function, but a matrix is actually a bracket. So you need to use both of those operators, if you will, or mathematical operators, to go ahead and indicate it. And what I'm going to do is I'm going to enter the coefficients. Okay. So this is 2, -2, and 4. So 2, -2, and 4. Close the bracket. I'm going to close the parenthesis. Oh, -4, I said, not 4. And my roots are -1 and 2. So if I was to write that, this here becomes, oops, S +1 times S -2, not +2. Oh boy. I guess my eraser button doesn't work on my pen. I'm going to have to change up my pen. That becomes S -2. That's what that equation becomes. Now, interestingly enough, I entered in my roots here of 1, -1, and -2. Why did I end up getting the same output out of MATLAB as I did? I showed up on the screen here. I didn't enter in 1, -1, and -2. I entered in -2 or +2, -2, and -4. Yeah, you just divide by 2. So I can divide the 2 out. You don't even have to. You can leave it in and it'll end up getting the same results. Okay. Because if I move a 2 out front over here, it doesn't change the fact that the roots are always going to be S +1 or S -1 and +2. Okay. One last thing about using the roots, make sure your coefficients are in order from highest to lowest, and don't skip. What I mean by that is if I have S cubed plus 2S squared plus 5, you'll notice that I don't have an S to the 1 term, right? In MATLAB, the way that I would enter that is 1, 2, this is where I don't have a coefficient, but I do have a coefficient. It's 0, isn't it? this is the same thing as saying this. Right? So you can't just throw that zero coefficient away, because MATLAB will just say, oh, if you just gave me 1, 2, and 5, that means it's s squared plus 2s plus 5. But in actuality, you have an s cubed. So I think that also applies, well, maybe not in C-solve. Didn't C-solve on your TI, do you actually enter in the whole expression with s terms and everything? Okay. It probably has a similar feature where you can do roots, I don't know, but I just find it easier to do in math. And does anybody want me to see me how to do the roots? Well, let's do the roots because you have complex numbers and it gets a little bit confusing. So we're going to enter in the roots of the denominator. We'll find the roots of the denominator entering the polynomial coefficients here. So we have roots of 1, 5, 8, and 6. Close the brackets. Close the parentheses. And now you can see that I have a -3 plus 0 times j. So MATLAB, what it tries to do is it tries to give you results. So it'll twist itself in knots to go ahead and give you whatever number it can, including complex numbers. Once it's gone ahead and done complex numbers now, it just assumes that all the numbers are complex. So -3 plus essentially 0i is really just -3. And then the other key point about this is you have complex numbers, right? -1 plus j and -1 minus j. You remember what we talked about in this class. You must have complex conjugate pairs to be able to do this work. So you can see that I have complex conjugates. It's -1 plus or minus j. So over here, the roots are, or the expression of the denominator becomes s plus 3. And then you have, do you remember how we wrote it in when we were trying to get it standardized? We said s minus the real part, quantity squared, plus the imaginary coefficient squared. Okay? That is exactly the same as s plus 3 times s plus 1 plus j times s plus 1 minus j. That's what we have over here. Okay. Now be careful. So this form here is much easier for us to do our pole zero map than this one. This one, you got to understand how to set that up a little bit to make that work. So if you're looking for pole zero maps, just bring it down to fully factored form. If you're bringing it to going back to the Laplace table and actually bringing it back to the time domain, this one is a lot easier to do. Because remember, if you did this one becomes e to the -1 plus j, right? In the time domain. That's really difficult in the time domain because you have a j term in there which doesn't exist in the real world. So then you have to multiply by you have to add the terms up, you get complex conjugates. It becomes a whole, a lot more math. So using the top one is a lot better. Now we can build our pole zero map. And MATLAB will do that for you. Numerator, denominator, sys, which is your transfer function. And then you can actually have a pole zero map. All right. You'll notice though, when I do it over here, the only problem that this doesn't have is it doesn't have that multiplier of 2 up front. Okay. So you have to be careful. This just ignores that multiplying coefficient. So I can't take this back in the time domain, which is okay. I'm just trying to get the transfer function. So let's go back to MATLAB. So I'll say my numerator is equal to, and this is just defining a matrix called numerator or num. That's my numerator. My denominator is equal to, again, the coefficients. Now my transfer function, and you actually have to have, I think it's the linear systems one here to be able to do the transfer function, but I'll define my system and you can pick this anything you want. You do a transfer function call. Oops. my parentheses, and then I just pass it the numerator and denominator. And it's going to return the actual original transfer function minus that 2 coefficient that I had up. You see how this doesn't have the 2 times s minus 2s minus 4? If you wanted to go ahead and get exactly the same thing, if you plug this in, so go without factoring it. Now we'll do our system. Now you get the same result. So one, I'm only looking at the pole, the zero map, and the other one is I'm actually trying to replicate the transfer function. So if you want to actually show what the transfer function is, you wanted to do some other stuff. There's something called a linear time invariant function that's built in the MATLAB that'll give you characteristics. We'll see that at a different time, but you would actually do this one. So now, what's that? You don't need it because I'm just doing a pole zero map. But the nice thing is, if you enter it with the 2's in here, you're going to get exactly the same pole zero map. MATLAB is smart enough to plot out once it comes out. Guess I'm low on system resources. It's been a while since I rebooted, so hopefully it wakes up. Here we go. And there's my pole zero map. So you can see this is the j omega axis, the dashed line here. This is the sigma axis or the real axis. And it shows I've got my complex poles here and my real pole here. It also shows the zeros. I have a 0 here and I have a 0 there. Okay. And does anybody have any issue with the fact that this imaginary axis, the units are inverse of seconds? It's s to the minus 1, right? Seconds, oh, it's 1 over seconds. What is the S-plane plotting again? It's frequency, right? And you can go from radians per second, right? It's plotting radians per second. So technically this should be saying radians per second. For the j omega axis and for the real axis, it should be seconds, right? Because it's e to the minus alpha t, correct? So alpha and the t term have to have the different, the units that cancel each other out. So this is really seconds. This technically should be radians per second. I don't know why MATLAB doesn't do it. So a nice, quick, convenient little way to do it. And I just showed you how to do it in MATLAB real time so that you can see, all right, you're not BSing me that you're actually able to do this stuff. We entered it almost exactly like this, and we were able to get the same results. Again, you just have to have in MATLAB, and I'll show you this real quick if you haven't had it set up. So for MATLAB, you have to add in, and your add-ins in here. And this, you probably did this already in lab. Hopefully this comes up, but you'll actually see what the add-ins are. So I've got Simulink and the control systems toolbox. If you don't have the control systems toolbox, PZ maps doesn't exist, TF doesn't exist, you wouldn't necessarily have that. Okay. I only include this optimization toolbox because in my power class, we actually say, hey, go ahead and do nonlinear solving, and you have to use an optimization tool to do that. I also do the symbolic stuff because sometimes it's helpful to do it, but I hardly ever use the symbolic. The one I will use a lot in this class is Simulink, and then the control systems toolbox, but I don't have a ton of add-ons. So, oops, I guess I should do updates. No, forget that. Okay, questions on this? Kind of sort of making sense? Okay. So you can see that as S approaches 0, right, we get a pole or a 0. So S gets that. What about our less obvious poles? So if we take this limit as s approaches 0, g of s, we end up with a function like this. And when we're done, we end up canceling out the s. We end up, when it approaches infinity, whatever the highest order s term is in the numerator and denominator dominate. So what we end up having is an s squared in the numerator and an s cubed in the denominator. So with our limit function, we end up with 1 over s as s approaches infinity. And that becomes 0. That's our infinite 0, right? Because the transfer function either has to approach infinity or 0 for it to be a pole or a 0, respectively. Doesn't this approach a 0 at s equals infinity? So if I really want to append that, I actually will add another 0, and I'll just write s equals infinity over there. And why is that important? Because we talked about this, the number of poles equals the number of zeros. Oop. Very important. You always have the same number of poles as zeros when you include infinites. Okay? And why that's important is when we start doing root locus, your root locus plots might kind of look like this. And what we do is we start at these poles, whoops, this way here, and we end at zeros. So if we didn't have that s equals infinity 0, how could we ever end at a 0 if we never had a 0 to end at? Right? If we only include the finite ones, we only have 3 poles and 2 zeros, so we're short one. But in reality, we have that third 0 at s equals infinity, so we can do something for root locus. So giving you a sneak peek at when we look at root locus. So just a summary there. So last little bit on this topic is if we have a function here where we have a pole, transfer function that we see here, and it's all going to be accurate, meaning it's all going to be in the left-hand half plane because all those poles are in the left-hand half plane. We see that we hit it with an input, which is going to give us a steady state function. And then these 3 here are going to decay with time. So I can do my partial fraction expansion, but I'm not going to actually do that because I don't really care what those are at this point. So then I have a K1 term, which is my steady state response. And then my K2, K3, and K4 are all decaying exponentials. Out of the 3, which one is going to decay faster? K2, K3, K4. Hard? K4? Here's what I would say. An easier way to look at this is just a suggestion. This becomes, the first one becomes this, right? Because 2 is the same thing as 1 over 0.5. And the next one is 0.25, right? Because 1 over 0.25 is 4. And this one is, because 1 over 0.2 is 5, right? I'm not doing anything crazy. And these numbers here are all taus. So the question is, how many time constants does it the system take before it reaches steady state? Generally say about 5 time constants. So if I look over here, 5t1 is greater than 5t2, which is greater than 5t3, right? 5 times 0.2 is 1. 5 times 0.25 is 1.25. And 5 times 0.5 is 2.5, right? So remember, the time constants as a unit of seconds. 5 time constants are when it reaches steady state. That decays first because it only takes 1 second to go bye-bye. That's number 2. And that's number 3. So if I was to do my pole 0 map over here, and I'm just going to look at the poles for the time being. The closer you are to the real axis, the longer it takes to achieve steady state. The further away, meaning farther away from the J omega axis, it takes less time to reach steady state, right? So I find this to be way more helpful because just looking at this number here, -5, doesn't tell me anything. But when I put it in terms of a time constant, which is what us electrical engineers are very comfortable with, then it kind of screams at you saying, hey, we know it takes 5 time constants, and my time constant's 0.2 because it's e to the minus t over tau, or e to the minus t over the time constant. Then I can see, oh, 5 times 0.2 is less than 5 times 0.25, and on and on. So goodbye first, second, and third. So if you really want to have the system achieve steady state, you have to wait for this one to decay away. That's the slowest pole. So if you want fast system response, you're going to try to figure out how to move those poles that are closer to the J omega axis more to the left, if reasonable. All right, so let's take a look at my time. We have time. We'll at least cover the first order system time constant, and then we'll see where we are for second order. So this is just kind of a summary of our first order time constant. First order time constant, our pole 0 map, has only a pole, one single pole, and it's purely real. So it means it lives on the real axis. And we're going to assume that it's a stable one, because we eventually want it to reach steady state, right? And if it is in the right-hand plane, then what ends up happening is it never achieves steady state because it just continues to grow. But a left-hand plane does actually achieve steady state. So our transfer function has a form of this. So it doesn't matter what the numerator is. We're really focused on the denominator. And if we hit it with a unit step, means it gives our S over here, we end up with an expression that looks like this: 1 minus e to the minus alpha t. Okay. And if you recall, at each step along the way, or each time constant, I get closer and closer to steady state. At one time constant, right? 1 over a, because a here is in the numerator, and my time constant would be 1 over alpha, would really be the time constant. So at one time constant, or 1 over a, I get to 63% of the final value. So almost 2/3 in that first jump. Because it's an exponential, it goes much slower. So at 2 time constants, how do I evaluate that? Well, how do I evaluate 2 time constants? It's exp of -2, isn't it? Because 2 time constant means t equals twice the value of our time constant. So 2 divided by 1, because the time that's 2 times the time constant, is just e to the -2. And if I go 1 minus the answer, I'm at 86.5% of my. And then when I go 3, so let's do 3. 95%. So some people will say that 3 time constants is sufficient because you're, you're in 5% of your final value. Some people say 5. Now we're at 99.33%. And if you really need super precise, I've not seen it a lot, but I have seen people talk about 7. 99.9% of the way there. So we'll split the difference and we'll call it 5%. So at 5 time constants, we're at 99.5% of our final value. We're good to go. So we're going to develop a bunch of equations based on a first order system. And we're going to use these equations, TC, TR, TS, all that stuff. We'll use them fairly extensively. So the first question, the first term we're going to define is T sub C, which is our time constant. And that's the time it takes to reach 63% of a final value or steady state value. And that's an easy one. That's just 1 over the whole of that expression that you're looking for. The response time. So this is a characteristic. This is a definition. This is an IEEE definition. How do you know if something is about 90% of the way there or close to being done? We know it never gets to 100% because it's an exponential. So we can't say, hey, it takes 10 minutes to get from 0 to 100% because it never gets to 100%. So we pick 90% of our final value because that's getting close to it. So we, you know what, we're at 90% of the way there. That last 10%, we're not going to worry about it. Why would we pick 10% as our starting value? This is a more subtle answer. Why do you pick 10% and not 0%? The less obvious answer is if you live in the real world and you have a meter or device measuring this parameter, is it always going to stay at exactly 0? Or is it going to bounce around a little bit? It bounces, right? It doesn't stay at 0. It goes up and down a little bit. It's hardly ever going to be 0. It's going to be a non-zero number, probably a positive number, but it's not going to be 0. And it kind of floats around. So the reason why you pick 10% is once you assume to get above 10%, I've started doing something. I'm at least 10% of my range. I'm not having some measurement inaccuracy or something like that. It's going up. So I start with 10% because that way I'm confident that I'm on my way. So my rise time is calculated to be pretty, reasonable number of how long it takes to go from 10% to 90%. Okay. And then this is just math, right? We want our final value to be 90% of its initial, of its steady state value. And the first time to be 0.1. So we solve these two equations because they're decaying exponentials. We do a little bit of math. And we end up with T2 as 2.31 divided by A. And 0.11 divided by A. Then we just subtract them. And we end up with, oops, there's a typo here. Sorry. Let me fix this. It's not 2.13. It is 2.31. Ah. Sometimes that happens. Fast fingers, fat fingers, whatever you want to say it. So it's 2.2 divided by A. That's approximation, and that is close enough for what we're trying to accomplish. Okay. Now, the next parameter that we're going to do is called settling time. And so that's how long it takes for us to reach its approximately 2% of its final value. You can do 2% or 5%. We'll do 2% in this class. So 2% corresponds to 98. And this one, we're going to say, we don't necessarily know the starting time. We're just going to say it settles out in a certain amount of time. So if we have some way of triggering a system, we can start our stopwatch and the system should reach 98% of its steady state in this amount of time. So same math step. We set it equal to 98% of its final value. And we solve for our settling time. And we get approximately 4 divided by A. Right? Those are our 3 equations that we'll use because what we're going to do is we're going to actually start picking our value of A to meet certain parameters. We want our settling time to be less than 10 seconds. So if we know what TS is, we can solve for what A needs to be so we can build our system that meets that value of A. So with our step input, it's usually the worst case scenario for a first order system. So if we hit it with a step input, we can sort of back calculate what our transfer function needs to be. So if we hit it with a step, we have, whoops. Our transfer function here, we hit it with a unit step, and then we go back to the time domain, we have it over here. So now we want to do is we want to find our value of A by find the amount of time that it takes to reach 63% of its steady state value. And we want that to happen in 0.33 seconds. So we can solve for our value of A equal the 7.7. That's our value of A. We also want our steady state value to be 0.72. So when we go back to the time domain, we know that K over A needs to be equal to 0.72. So we define K over A equals 0.72. And then we can use our time constant, and that has to be less than or equal to 0.13 seconds. So you can solve for A with this equation, and then you can solve for K with that equation. So we just designed a system to meet two criteria. We want our steady state value to be less than 0.72, and we want it to get to we want it to have a time constant of 0.13. So this would be a design. Somebody would walk up to you and say, hey, can you design this whatever to meet these two criteria? So our final transfer function is 5.54 over S plus 7.7. And this is what we're going to do for the most part for the rest of the semester, is designing systems, not just analyzing the systems. We're going to come up with design parameters that we need to meet. And then that's where we have it, because we have all our modeling done. We know electrical circuits, mechanical circuits, thermal circuits. We can do all that. Now we just have to go ahead and pick a lever length or design some RC circuits, et cetera, et cetera. All right, I only got about 10 minutes, so I'm going to end, or I'll pause to see if there's any questions on anything before we get into second order systems, because second order systems have a lot more parts and pieces to them. It has damping ratios or damping coefficients. It has settling times, rise times, and you have very different calculations for some of those. So I'm going to pause here to see if there are any questions. Let's see if we have any chat questions or comments. Nothing? Okay, well, just as a pitch, if anybody's interested in rooting on one of your classmates, the Orono high school basketball team is playing at the Pit tonight. They're playing Old Town. They're supposed to be two really good teams. So if you want a high energy environment, and I think it's going to be free to get in, I believe so. That's the Pit, which is in the old gymnasium. So you can cheer on one of your classmates is one of the assistant coaches on Team Orono. So you can go root them on and give them high fives if you want. I'll probably be there with my kids to cheer everybody on, but should be a fun thing if you want to root and support one of your fellow classmates. That's not part of the assignments. That's just doing nice things for your classmates. What's that?
Do that, so it'll work good.
Bring your homework with you. We can do both. Actually, Old Town has a better record than Orono. Orono high school boys basketball team won the state championship last year in their class. But this year, they've had 3 losses. Old Town team has only had 1 loss, I believe. Cooper Flag was in Nokomis, and he's gone. He was only here for a year, and he plays in Florida. He's too good. Actually, he's skipping his senior year. He's good enough that he's going after his junior year right to college. I don't know how it works, but this is, once you get to that level, basketball is a business. It's not about having fun. It's
how to go about, like, because apparently said like structure, like it's the NCAA go on high school tournaments.
oh,
Like,
could be.
they're putting regulations on the team because they're winning much so good.
Oh,
Like getting back with the coach and you want to apply on Vegas.
Oh. You got to be careful because then if you get any of that money, you can lose eligibility, because I think in college it's supposed to be an amateur. But now they have licensing deals and all that stuff. So the rules have gone so complicated, which makes sense. The athletes should get paid. Because of licensing, but I don't know if they're still considered amateurs or not. It's a business. College athletics, even here at UMaine, is a business. The main hockey coach just got a big pay bump. He makes more than the president of this university. And I'm not saying he shouldn't. I'm just saying it's like, if you think about the economics of it, you know, you would imagine that the president has more impact on the bottom line than the men's hockey coach. And I'm not saying he's not worth the money. It's just that, you know, that's supply and demand, right? We live in a capitalist society. So people have to pay, you know, whatever they have to pay to get that. But I think the highest paid person on campus is the hockey coach. And if you go to the big time athletic programs, even if you go to like Alabama, the highest paid person in the state, everybody in the state that's a government employee is the football coach or the basketball coach.
So just like fire, instead of paying like tens of millions of dollars, it's like. all right,
That's the contract though. A contract says if you got a 5-year deal, you got to pay me every 5 years. If I'm terminated, then you got to continue to pay me.
So like 3 years left. And.
That's all contract stuff. You're talking about, like I said, it's business, so. All right, well, there's no other questions. Have a great day, y'all, and I will see you, if I don't see you the rest of the day, see you tomorrow. Take care, everyone.
Thanks, Paul. I'll see you later.
Thanks, guys. Have a good one.